Well, hello everybody. So, we continue with our discussions on the introduction of multiphase flow. So, I had already discussed in my last lecture, I had already discussed the typical flow patterns which occur when gas and liquid flows through a circular pipe or through any particular symmetric, which can be a rectangular pipe, more or less the same flow patterns, or a square pipe also the same flow patterns are seen. Now, suppose instead of air, water, I introduce maybe an oil. It can be kerosene, it can be toluene, it can be anything. I introduce another oil. Do we expect the same flow patterns to exist? See, one thing is for sure, gravity in this case also will be trying to pull the lighter phase towards the top, heavier phase towards the bottom, right. So, therefore, at low flow rates, we have the stratified smooth, then as we increase the phase velocities, we have stratified wavy. Now, if you remember in my last slide, what did I get? Sorry, in my last slide, from here when I increased the phase flow rates, we found that there were some points where the waviness of the interface was so much that it was touching the upper wall, as a result of which plugs were formed and it resembled the slug flow pattern observed in vertical tubes, although it was an asymmetric slug flow. Now, in this particular case, if you find, we find that due to the higher surface tension of the liquid, it cannot assume the shape of the elongated plugs as we observe in gas liquid cases. On the contrary, when the waviness is very much, then it shears the interface, and therefore, there is a large amount of droplet of both the phases entrained at the interface between a continuous kerosene phase and a continuous water phase. This did not happen for horizontal air water flows, but in this case it happens because the liquid, they tend to remain spherical and they cannot sustain, or they are not stable at an elongated shape. So, therefore, after stratified smooth, stratified wavy, instead of slug flow, we get a 3-layer flow pattern, and as we increase the velocity, we find that one phase gets dispersed into the other. Now, here I have got a very important point to tell. While we were discussing gas liquid flows, repeatedly I have been telling you that, well, when there is less gas, large amount of liquid, we have bubbly. When we have large gas, less amount of liquid, we do not have droplet, we have annular. Why? Because the liquid phase can wet the pipe wall, the gas phase cannot wet the pipe wall. But when we are having two liquids, either of them can wet the pipe wall. It depends upon the hydrophobicity or the hydrophilicity of the pipe, like which phase will have a greater tendency to wet the pipe wall, but you must remember that either of them can wet the pipe wall. So, therefore, just like we can have oil droplets in water, we can also have water droplets in oil. Therefore, in a vertical pipe, what do you find? A pipe say of 1 inch diameter or 25 millimeters diameter, when the oil is in a smaller proportion compared to water, we have oil droplets dispersed in water. As we increase the oil velocity, the oil tends to take several irregular shapes, but if the pipe diameter is not very narrow, it never assumes the axisymmetric bullet shape, which we observe for case of Taylor bubbles of air. They take some irregular shape, and finally, if we increase the oil velocity more and more, a time comes when the oil becomes the continuous phase and water gets dispersed in it. Now, this is a unique phenomena which occurs for liquid-liquid cases. It does not occur for any other two-phase flow situation. And this particular phenomena of the continuous phase getting inverted to the dispersed phase and vice versa, this is known as phase inversion. So, during phase inversion, we find that one phase it tends to become continuous from dispersed and the other phase tends to get dispersed from continuous, and this unique phenomena of phase inversion, since it is concerned, or rather since it is associated with the making and breaking of a large number of interphases, it is usually associated with a large amount of pressure drop and a high degree of turbulence or mixing. Well, this was for adiabatic conditions. Now, suppose we go for a heated tube where maybe a single component, say a liquid is being introduced and heat is being supplied from the walls, and as it flows up, change of phase occurs. Now, what happens in this particular case? The tube is heated, maybe say subcooled water is coming in. So, initially we have single phase liquid in this particular case. Then as the liquid starts getting heated, bubbles start forming. Bubbles will start at some nucleation sites at the wall. Moment the bubble starts forming, it will remain attached to the wall for a very short time, and then it starts getting detached and it rises due to buoyancy as well as due to flow of the liquid. So, therefore, we get something like the bubbly flow pattern. Now, again, as this particularly heated liquid or this particular two phase mixture it starts flowing up, we find that more and more bubbles are formed. As more and more bubbles are formed, they come very close, they start coalescing. Moment they start coalescing, naturally the vapor bubbles, they will assume their stable shape, which is nothing but the axisymmetric bullet shaped sort of a thing, or the Taylor bubble sort of a thing. So, therefore, the slug flow sets in, and then from slug flow, as more and more amount of liquid gets vaporized, so large number of Taylor bubbles form. So, naturally they coalesce with one another, and when they coalesce, they form a continuous gas core, and naturally they push the liquid to the sides. It forms an annular flow pattern. If heat is continued and the tube is long enough, what happens? There is annular flow with a liquid film which is being heated and a vapor core in the central region. Now, this liquid film, it keeps on getting depleted due to two reasons. The first one is because of vaporization, some amount of liquid film it gets vaporized into the vapor phase, and secondly due to interfacial shear, which increases as more and more amount of vapor is formed and as the vapor velocity increases. So, therefore, this interfacial shear also increases, and the liquid from the film gets sheared as droplets here. Possibly then after that, in a heated tube we get the droplet flow pattern, which we did not get for adiabatic cases, and finally, when all the liquid has vaporized, we get single phase vapor flow. So, therefore, what we find when we are dealing with a heated tube, then we find that there is departure from thermodynamic equilibrium, also there is a radial temperature profile. Now, due to these two reasons, we find that the flow pattern it changes inside the tube, which did not happen for an adiabatic case if all the input parameters were kept constant. Firstly, the other thing which we find is that in this particular case, if you observe the flow patterns, there are two new things. One is churn flow, which was very prevalent when we were discussing your vertical air water flows, is not present here. The other thing is droplet flow comes into picture. Now, this was the case of a vertical heated pipe. If we simply make the pipe horizontal, keeping everything else constant and introduce water here, the factors which were there for a vertical pipe, namely radial temperature profile, departure from thermodynamic equilibrium, will persist. Along with that, asymmetry due to the gravitational effect sets in, and the situation tends to get much more complex, with the possibility of intermittent drying and rewetting of the upper surface of the tube. So, in this way, if we keep on proceeding, we find that more and more complex phenomena, or more and more interesting phenomena I should say, sets in as we deal with other combinations of two phase flow situations. So, therefore, from this you have understood that what are the basic difficulties of analyzing two phase flow. the basic difficulties are two. Number one, the two phases can distribute themselves in a number of ways, as you can see. That depends, as I have already discussed, it depends upon the conduit geometry, the conduit inclination, the direction of flow, phase physical properties, and so on and so forth. And this is not under the control of the experimenter or the designer. Along with that, what do you find? That definitely with the interaction of the two phases changing, the interfacial shear changes, and we have to remember the most important thing, that the two phases have different densities. As a result, the lighter phase tends to slip past the heavier phase. Due to this, if you have introduced the two phases at a known composition, the same composition does not exist when the two phases are flowing inside the pipe due to the existence of this slip. Or in other words, if we are talking about air water mixture, the in situ void fraction will not be equal to the inlet fraction of the two fluid, or rather of the two fluids. So, therefore, what does it imply? The first thing which it implied is that the two phases, suppose for the time being we assume them to be air and water. So, these two phases we find that while they are flowing, they have one particular void fraction, say alpha, inside the tube. How do we define this alpha? This is the, say, the proportion of the gas phase, or rather the volume occupied by the gas phase divided by the total volume of the pipe. Okay? And this will not be equal to the inlet volume fraction, which we define as beta. So, therefore, this is the in situ void fraction and this is the inlet void fraction or the inlet composition. This will depend upon the inlet flow rates. If we denote Q with the flow rates, then this is going to be Qg by Q total, which is nothing but where Q total equals to QL plus Qg, right. Now, due to this, several problems arise. What are the problems? Suppose we would like to analyze this two phase flow situation. The analysis will be just the same as the single phase flow of any particular fluid through a pipe. Now, if we go for single phase flow, say let us develop the momentum equation. I will not be going into the details of this. Suppose we are having, maybe say we consider delta z portion or delta z length of the pipe of cross sectional area A, and here we find and maybe the wetted perimeter as S. So, in this particular case the pressure is going to, or the pressure force is P A, and in this particular case we find that the pressure force is P del Z into delta Z into A, right. And here we find that the gravity is acting. So, there is a component of gravity in this particular direction. So, if this is rho g, the component of gravity will be rho g sin theta, and since flow is occurring in this particular direction, there will be interfacial shear. So, if we consider the forces which are acting on this particular fluid element, namely the pressure force, the body force and the wall force, which is given by tau, the wall shear is given by tau w, and if we equate it with the rate of change of momentum, then what do we get? We get a pressure drop relationship. I leave it as an home assignment to perform this particular balance and then finally arrive at an expression to find out the pressure gradient. This expression is tau w S by A plus say rho g. If the pipe is inclined, then we have a sin theta component where theta is the angle with the horizontal, plus this gives you d dz of u into say g, where g is the, or rather I will put it as w by A, where g is the mass flux which is equal to the mass flow rate divided by area, in other words W by A in my set of nomenclatures. So, this was for single phase flow. Now, suppose instead of single fluid, say for example, two fluids are flowing here. So, what do we find for this particular case? What are the things? Let there be any sort of distribution here. So, what happens? These two fluids, no matter in whatever they are mixed, they will be interacting with the wall. So, therefore, this is going to become tau W two phase, some sort of interaction with the wall, and instead of single density, it is going to be a mixture density, and this u, it is going to be a mixture, rather a mixture velocity, right. If the two phases are completely mixed, then this equation is fine, we have a GTP here as well. And if they are separate, then in that case the equation, what it should become, there should be tau W1 S1 by A plus tau W2 S2 by A plus rho TP G sin theta plus ddz of, say one fluid is G1, one fluid is denoted by 1 and the other is 2, we get something of this sort. Now, when we try to evaluate the pressure drop using either of them, what do we find? First thing which we do not know is rho TP. On what does rho TP depend? It depends upon the in situ void fraction. Mind it, it depends upon the in situ and not on the inlet void fraction. Inlet void fraction is a known parameter, but in situ void fraction we do not know. And rho Tp, it is a function, it can be expressed as, if alpha is the void fraction and say for a gas liquid system, my phase 2 is gas, phase 1 is liquid, then what do I get? Rho Tp should be equal to alpha rho 2 plus 1 minus alpha rho 1. So, for finding out the gravitational pressure drop, we need to know alpha, and alpha is in no way related in a straightforward fashion with beta. This is the first problem we face. What is the next problem that we face? How is tau W Tp related, or rather how can it be evaluated? Can we define something like a two phase friction factor? Then in that case, how is this two phase friction factor related with a single phase friction factor which we have? So, this is also not very much known to us. The other thing is, if we are defining UTP, say, so this U, it is a function of, say, mass flow rate, density and area, right. So, therefore, sorry, for single phase flow, it is related in this particular way. If we are having two phases, the two phases are having different velocities and they are in no way related to the velocities at the inlet. Say one fluid has a velocity u1, other has a velocity u2. So, therefore, what is u2? It is W2, the mass flow rate which is definitely measurable, rho 2 by A2, where A2 is nothing but, it can be written down as A into alpha, the void fraction. So, therefore, in order to find out how your u2 is varying with length, you need to find out, you need to know alpha. So, therefore, we find that if alpha cannot be determined from input parameters, which it cannot do, it adds to the additional complexity of two phase flow. Just the way I was discussing till now. So, therefore, if we can write it in this particular way, we find that rho has to be written down, or it has to be substituted with rho Tp Here of course, I have defined it as rho m, the mixture velocity. You can do whatever you wish, and we find that it is essential to have an estimation of void fraction, as I have already said. There is no obvious relationship between wall shear in single and two phase flows. We also find that S, it includes S1, the wetted perimeter for phase 1, S2, the wetted perimeter for phase 2, and apart from S1, S2, there is also an interfacial area where the two phases interact, right. So, therefore, we find that even for finding out the simple pressure drop also, it becomes difficult. Why? Number one, the two phases can distribute in a large number of ways, and unless we know the distribution, we cannot find out tau W1, tau W2, we cannot find out S1, S2. And again, depending upon the distribution, the void fraction is going to be decided, and unless we know the void fraction, we cannot find rho Tp or rho m. So, therefore, this suggests why the two phase flow becomes much more difficult as compared to single phase flows. The reasons primarily being there is the existence of multiple deformable and moving interfaces. There is a multi-scale physics of the flow phenomena. There is significant discontinuities of the fluid properties and complicated flow field near the interface. You can very well understand that near the interface you suddenly shift from liquid properties to the gas properties. In addition, when we have one phase as the gas phase, for example, for gas liquid flows, vapor liquid flows or gas solid flows, the compressibility of the gas phase also comes into picture, and definitely there can be different wall interactions for the different fluids. So, therefore, we find that when there is one phase present and we just introduce the second phase, the situation becomes much more complex, because the two phases interact not only with the wall, but also among themselves. Accordingly, they distribute in a wide variety of ways, and since the two phases have different densities, the lighter phase tends to slip past the heavier phase, as a result of which the in situ void fraction is different from the inlet composition. Inlet composition we can manipulate, but in situ composition there is no straightforward way of finding out the in situ composition. Again, this in situ composition depends upon the distribution. Definitely, if you have some, or if you have devised some particular way of finding alpha in bubbly flow, you cannot use the same relation to find alpha for annular flow. Or if you have some particular relationship to find alpha for gas liquid bubbly flow, there is no guarantee that the same relationship can be applied for oil in water dispersed flow. So, therefore, with these things I think you have got a fairly good introduction of multiphase flow, but before I start, I would just like to show you, or just like to discuss in very brief the terms which will be coming across frequently. My reason for discussing these terms are, see, you have come across these terms, but maybe not the same nomenclature. If all of us we use the same nomenclature, or in other words, suppose I have a unified nomenclature, then at every point I do not need to define those things. For example, as far as I am concerned, for me the mass flow rate will be denoted with W. Now, let me clarify one thing at this point. You are free to use any other nomenclature, but in that case you have to define your nomenclature. Normally, as chemical engineers or mechanical engineers, we define mass flow rate as m dot, but for this class I prefer to keep it as W, volume flow rate as Q. There is one particular term which we do not come across much when we are discussing single phase flows, but we will be coming across quite frequently in two-phase flows, that is the mass flux. Just like heat flux, mass flux, it is the per unit mass flow rate per unit area. Pipe diameter D, cross sectional area A, wetted perimeter S, these are all fine. The corresponding terms in two-phase flow are naturally, we have got two phases, so there are two W's and a total W. We have two Q's and a total Q. We have two mass fluxes and definitely a total mass flux also. Along with the cross sectional area, we need to know the area occupied by phase 1 and phase 2. We need to know the wetted perimeter, which is rather the perimeter which is of the wall which is in contact with phase 1 S1, which is in contact with phase 2 S2, and of course, there is an interfacial area as well. As a consequence, what do we find? We find that there are 4 velocity terms instead of 2, because u1, u2, they are the local or the in situ velocities. So, therefore, in situ velocity of phase 2 and this is the in situ velocity of phase 1. So, by definition, u2 should be equal to q2 by a2, this should be q1 by a1. Now, what are these a1, a2? They are the cross sectional areas occupied by phase 2, cross sectional area occupied by phase 1. So, naturally, this can be defined in this particular way, this can be defined in where alpha is the void fraction or the fraction of phase 2. So, therefore, along with these two, just because we refer to velocity of the fluids very frequently, so therefore, what we will prefer to do, we will also prefer to define two other velocities which are known as the superficial velocities, where this is the velocity which the fluid will have if it were flowing alone in the pipe. So, therefore, these are measurable parameters, they are just your volumetric flow rates divided by the cross sectional area, because they define the velocities which the fluid would have if they were flowing alone in the pipes. So, therefore, these are inputs while u1 and u2 are outputs. So, therefore, just as I have mentioned, the additional terms are definitely in situ void fraction, the inlet volume fraction, and the other important thing which I forgot to tell you is the quality, which is the weight fraction of phase 2 in the flowing mixture. This x varies in a heated tube and it is a constant for an adiabatic condition, right. Now, before I end, I would also like to specify one particular thing, that by convention my lighter phase or the dispersed phase, I denote it as phase 2, and all the properties including void fraction, inlet volume fraction, quality, we define with respect to this phase. That means, for an air water flow, my air is phase 2 and water is phase 1. For kerosene water flow, maybe if kerosene is in a smaller proportion or it is the discontinuous phase, then kerosene will be phase 2 and water will be phase 1. And most of the properties we define in terms of phase 2, right. So, therefore, with this I complete my particular introduction of multiphase flow, and in the next lecture I will be discussing the rather the uniqueness or the specialities, it is not the uniqueness exactly, the specialities of two-phase flow through miniaturized systems. Thank you very much.